Well, thank you very much. I just wanted to mention that the talks this morning already have been so good that they're definitely tough acts to follow, especially right before lunch. So I hope you'll bear with me a little. I also feel like I have to tell a joke because Dr. Brody was so funny. I can't stand up here and be a dud. So what I'll mention is that you know you've been a scientist a long time when the school where you got your graduate work and the hospital where you did your postdoc have both changed names since you went there. So thank you very much. What I'd like to do today, let me just go back one slide. I want to talk in very general terms about some things you need to keep in mind to make sure that you generate high quality data on the CyTOF. And what I would like to do is touch on 4 points: panel design, sample preparation, assay optimization, and sample acquisition. And as you're all well aware, we could sit here for an entire afternoon, if not a whole day, talking about these things. So I'm going to be bringing up just a few points for each of these. I will also be here after the general session is over with the DEEB, so we're going to have kind of a roundtable discussion. So you can definitely get into these in more detail. So just recently on our Fluidigm website, we released a panel design application to full access to anyone who has an account on our website. And I just wanted to talk about this. As Adib discussed earlier in his talk, mass cytometry is really giving you that ability to do high dimensional studies. We're currently up to 35 probes from Fluidigm. And this lets you look at system-wide questions. Even though signal overlap in mass cytometry is small, we still have to take it into account. And what the panel design tool does is it tries to maximize signal and minimize signal overlap into any channels that we're trying to assign to low abundance targets. And then we also want to minimize signal overlap to and from any channels where the expression of a target is going to be variable. So a couple of things to keep in mind is we need some information first as we go into this tool. And the biggest thing from a researcher's point of view is having information about the abundance of the antigen you're interested in, knowing a little bit about the sensitivity of the CyTOF to given metals, and then where signal overlap actually comes from. So signal overlap can really come from 3 different places. The first 2, impurity and oxides, as Adib had mentioned earlier, they're standard. We can predict these, and they're not going to change over time. One is impurity, so that isotopes that we utilize may not be 100% pure, depending on which isotope you use. Oxides are formed in the plasma by an ion from one of our metal tags binding to an oxygen atom. And then we have abundance sensitivity, which is a function of the mass spectrometer itself, where you can see a little bit of signal into the channel before and the channel after the metal that you're looking in. And I will mention, for those of you who have the 2nd generation instrument, CyTOF 2, this is very minimized. It's definitely down on the lower end with a maximum of about 0.3%. So the way that we define signal overlap and try to minimize it in our other channels is we need to know about the signal that we expect from the channel where the signal overlap will occur. And then the percent of that overlap from that donor channel into the recipient. So it's really signal times percent overlap. And the percent overlap is going to be the sum of the impurity, the oxide formation, and any abundance sensitivity. But as I mentioned earlier, because these values are constant within the panel design tool, we have a fixed matrix. So the way, in a very simplified explanation, the way that the panel designer works is that you input probes from either the Fluidigm catalog in which case the antigen abundance and the signal information is already going to be automatically included into the panel designer. Or you can enter reagents that you have produced yourself or markers that you haven't utilized yet but you want to assign channels to. You would then enter information about the signal expected from that marker, and then the panel designer will generate a panel that minimizes signal overlap into these very important low signal targets. What you get after that's done is a panel wheel, and the fins on the wheel, there's one for each of the metals, and the color gives you an idea of the signal overlap into a given channel, and that can either notify you that there's a potential issue with that channel. Maybe you may want to switch markers around, or it may be just something during your assay optimization that you have to look at that signal and see if it's going to be good enough, get enough resolution within that channel for you to be able to see your antigen in that particular marker, metal. Once those panels have been created, you can save and share them with any collaborators. You can also go back in the future and redesign or create more panels from what you've already made. Okay. So sample preparation really depends so much on your cell type, what type of assay you're doing. And again, we can talk in more detail about this later in the afternoon. But one thing I wanted to bring up is one thing that we found in-house at Fluidigm is that something as basic as thawing your cells can have a huge effect on the quality of the sample that you end up running on the CyTOF. Frozen samples can really help you eliminate a lot of variability, but it's always good to do that fresh versus frozen comparison in case you get questions from reviewers. So what we've found is that the biggest thing for thawing cells is using the appropriate thawing medium, which I'll show you on the next slide, but also that you're doing a 1:10 dilution, taking the pre-warmed thawing medium up into a 10 ml pipette, dispensing 1 ml of that onto your thawing cells in the cryovial, and then aspirating that into the pipette again, forming a gradient. And what's critical is to dispense that really slowly over about 30 seconds back into the tube that you'll use for your first wash, and this helps to prevent cell lysis and release of DNA. In case that does occur, it's important that the thawing medium that you use contains some type of DNase, and we use benzonase. And also, in some cases, people like to add in EDTA, which also helps prevent clumping of the cells. I'd also like to talk a little bit about assay optimization, and I just wanted to mention that some of the tips that I'm going to discuss in this part of the talk came from Jonathan Irish's lab at Vanderbilt, and Brent Farrell will be talking later about research done in that lab, but they've really done, shared with us at Fluidigm some of their expertise in assay optimization. So when we think about our staining protocols, sometimes we're doing surface only. We don't have to fix first, and so there's no risk to the epitopes for losing antibody binding due to the fixation. If we're doing intracellular staining, cytokine staining is going to require a longer stimulation time. We're able to surface stain and then fix and perm, whereas with phosphostaining, we're doing a rapid stimulation for signaling, and we need to fix to lock in that phosphorylation, and we have to take that into account in terms of how it can alter our epitopes of interest. So if we think about where we're staining live cells, we may have titrated our antibodies for that situation. If we then go to a system where we have to fix before the surface staining is done, this is going to require a retitration of these antibodies. And there are some very good resources out there that will actually give you information about certain antibody clones and their response to different fix and perm buffers. And also, if you're doing both fixation and permeabilization steps, that can also require additional optimization. It's very important to titrate your antibodies, and when you're setting up a panel with many markers, if you had to titrate these individually, it would really be a mammoth task. So you can titrate multiple markers simultaneously. It's really a function of, in your given sample of interest, do you have enough of rare populations to do that titration simultaneously with your other markers? If you don't, you may have to work out other strategies. But as you're doing the titration, it's important to keep identity markers constant so that you can gate and make sure that your subset percentages are maintained across the different titrations that you checked. Sometimes people titrate using a mixture of cell lines if they have cells at very low frequency, for instance, in tissues like blood or lymph node. For doing titrations of phosphospecific antibodies, it can be helpful to have an artificial mix of positive and negative cells. So stimulating cells and then spiking in cells that were not stimulated as your negative population. And one thing that's just a nice tip is that if you use hydrogen peroxide, this can actually activate a large variety of phosphokinases, allowing you to titrate without doing multiple stimulations. Just like in flow cytometry, with mass cytometry, it's very important to be able to identify dead cells in your sample, specifically because dead cells love to sop up antibody like a sponge, and it can really confound your analysis if you can't eliminate dead cells in your data files. So at Fluidigm, we actually have two different live dead discriminators, cisplatin and rhodium. Rhodium is actually an equilibrium intercalator that binds to nucleic acid. So it might not be ideal when you need to do stringent washings, like after a permeabilization step. Cisplatin, on the other hand, binds covalently, and so you have nice, stable staining over time, even if you don't run your cells the same day that they're stained. Controls are extremely important. Again, whether you're an isotype control advocate or not, it's kind of like Democrats and Republicans. You're either one or the other, and never the twain shall meet. But isotype controls are really not feasible in mass cytometry because to run 35 isotype controls for one sample just kind of negates the whole purpose. So we need to use other types of controls. So one thing that's done by certain labs is actually spiking in a cell line, maybe of a different species of origin, that you can then gate out by using a specific antibody tag to assess nonspecific binding. You could also, within your sample, look at staining on cells that you know are negative for a given marker to help you set your gates. And in some cases, where the resolution of a low signal from the negative or some potential spillover is difficult to do, you may want to use metal minus controls. So these are similar to fluorescence -1 controls, and again, they can help you not only to gate difficult populations, but also to assess maybe when you're optimizing the panel at first where you may have spillover issues. Another possibility is that when you're doing functional studies that are going to require fixation, if you have a surface-only control where you do this pre-fixation, that can also be helpful. And always when you're doing functional studies, the most important control is your biological control. So, for instance, you're unstimulated against your stimulated population. So lastly, I'd like to finish up by just talking a little bit about sample acquisition. This is actually much more important on CyTOF than a lot of people think, and I want to go into a few reasons why that is. So just as kind of a rule of thumb, It's very important to make sure that you're washing out PBS in your last couple of washes with deionized water so that you prevent clogging of the nebulizer or any sample tubing. Just like with flow cytometry, if you minimize debris and clumps, this is also going to help to improve the quality of your data. Cell concentration is important when you're running on the CyTOF. And because debris is a factor as well, we recommend assessing the cell concentration with a visual method like a hemocytometer or an automated cell counter that allows you to change the parameters so that debris can be taken into account as well. I also have an account in New England where they actually have their customers do a quick run of cells on one of their flow cytometers to get an idea of concentration and how good the cells look by forward and side scatter, and also assess debris. In terms of background, we want to minimize barium in buffers so that we don't end up with that as background in our samples. Usually with barium, if you're using calcium, magnesium-free reagents, that will also get rid of the barium. If you are wondering if a buffer you're going to be using is going to contain barium, you can always give us a sample to the CyTOF lab and have them run it for you to assess how much contamination there is. We also would like to avoid lead contamination, and since glassware is a source of lead, we would want to avoid use of glassware altogether and use plastic instead. As I mentioned earlier, we definitely want to avoid clumps. Part of this is just to keep sample tubing and nebulizers from clogging. So you can filter them using the 35 micron blue cap filter tubes that you may be used to seeing near cell sorters, and do that right before you're going to load samples on the CyTOF. And then in terms of cell concentration, we would like to target a sampling rate of about 500 cells per second. So if we're running at 45 microliters per minute, we would like our maximum cell concentration to be about 500,000 to 600,000 cells per mil. One tip is that if you're really not sure, you want to make sure you're injecting the right amount, you could always do a small aliquot at 25% of what you think the right concentration is, and just do a quick run to see if you're in the ballpark. One thing I wanted to mention is that there is nothing on the CyTOF that is analogous to forward and side scatter on a flow cytometer in terms of identifying cells by size and granularity. It's a common misconception that when a cell goes through the plasma and is ionized, that the resulting ion cloud is somehow proportional to the size of the cell that originated from. And that's not the case, because the ion cloud actually has to diffuse, or excuse me, move from the plasma to the interface, at which point the ion cloud expands to about 2 millimeters. So whatever type of cell it's generated that ion cloud, the ion cloud, once it goes into the optics, the size is not proportional to the cell that originated it. So the reason that we are so firm about saying that cells need to be properly diluted is that when you have cells go through into the plasma well spaced, you get two distinct ion clouds. And even once those ion clouds diffuse, you still get a good separation of these clouds, and each of these will be a unique event within the data file. And that's just showing live data coming that you would see on the CyTOF, where you can see 3 individual cellular events showing up here. Now, if our concentration is too high, these ion clouds are going to be generated close together, and when they diffuse, an ion cloud fusion is going to occur, and we're not going to be able to utilize this data because we don't know what signal is coming from the first ion cloud and which is coming from the second. Now, this will always happen occasionally based on coincidence, But if you have a high cell concentration, this is going to happen over and over. Now we can eliminate these types of data events at analysis, but you can imagine that if you're running at too high a rate, you may end up excluding 60, 70% of your data events just because you ran too concentrated. And this is just showing some data that was actually collected a while ago on an original CyTOF. And this is just showing you that when you look at 3 different cell concentrations, 1,000,000, 500,000, and 250,000, you can see these clumps or ion cloud fusions being quite high at 1,000,000 cells per mil, going down significantly at 500,000 and even further at 250,000. So it really shows you that the concentration is going to have a big effect on the quality of the data and how much data you'll lose, because you are going to have to gate these cells out to be able to do your analysis so that you can focus on the singlet events. So I'd like to thank you very much for your attention and take any questions. And again, just reiterate that we will be having a roundtable discussion later this afternoon. So if I brought up any points that you want to discuss further, or maybe I didn't talk about something you're interested in, please come by and I'd be glad to talk to you about it. Thank you very much.
Coagulant matter? Does, for example, like EDTA chelate metal ions that you don't want chelated?
We use EDTA in some of our buffers, and it's fine because the metals are already chelated to a polymer. They're not going to be free, and just having the EDTA there is not going to affect that binding of the metal.
Thank you. I have a second question, and it's a little bit weird. And I'm not sure if this is the right forum to ask the question in. Given that something like 80% of all rare earths are found in China, do you ever fear that deterioration of relations between China and the US could actually invalidate your whole industry?
I don't know if Scott wants to speak to that. Not going to happen.
You know, we hear that a lot, and it's really not an issue. The isotopic, so the rare earths are used in semiconductor manufacture in large quantities. That's the principal use for them. The isotopically enriched rare earths come from other sources, and they're actually stockpiled in large quantities. And where they're not stockpiled in large quantities, we've actually gone out and bought the next 5 years' world supply. What was the other? Oh, the other point is that if there's a problem with the Chinese mines in rare earths, that's a business opportunity for people in South Africa and the U.S. because there are rare earth mines in the U.S. and in South Africa. They're just not used because they're not cost effective against the Chinese. When you're looking at enriched isotopes, the cost of the raw isotope, the raw metal, is negligible. It's the enrichment that's costly. For the semiconductor people, they are worried about it. You might have trouble getting computers, but you're not going to have trouble getting enriched isotopes.
And just one thing I would mention too is that we actually can get great signal from very small amounts of metal. So when we make batches of antibody, the amount of metal we're using is so small compared to some of these other industries that utilize the rare earth metals. But that's an interesting question. Thanks for bringing that up. Any other questions? I know everybody's probably thinking about their stomachs right now, right? All right, great. If you have questions later, we'll be here this afternoon. Thanks very much.